Now I have the chat also in front of me if you're asking me questions on my computer. Okay, very well. So where did we leave yesterday? So we were, I was trying to explain the basic ideas on how you come up with a iteration scheme, which is producing C0 solutions of the Euler equations, which are nonetheless highly irregular. At least we expect them to be highly irregular. Okay, so let me recall that what we are trying to show is the existence of a sequence of solutions to a perturbed Euler equation. So you can think about VQ and RQ as approximate solutions, and the distance to being a solution is measured by the divergence of a 3 times 3 symmetric matrix, which I call RQ. So this is kind of the defect to be an actual solution, and you have an actual solution if RQ is equal to 0. And you have the usual constraint divergence of VQ equals 0. Okay, and what we, so our aim is to construct a scheme with the property that say VQ plus 1 minus VQ in C0 is under control. In particular, we want actually this to be a convergence sequence so that we can say that VQ is converging to a continuous function. At the same time, we hope to send RQ in C0 to 0. Okay, and the limit is going to be our desired solution, which for which we will have some quite striking properties. Okay, and I was explaining how on the blueprint of what Nash does, if you interpret it as in a certain particular way, you can cook up a basic question in PDE, which would help you understand whether such an iteration is feasible or not. Okay, so remember, we are actually looking at perturbing VQ by adding some highly oscillatory perturbation. And let me actually put variables too. So the ansatz that we were trying was something like this. So we have an addition which is like, it has a certain particular form. So it depends on the previous iterate. Okay, and then it has a fast oscillating, two fast oscillating variables, lambda x and lambda t. And there's going to be a small correction, which I have already treated and I'm not going to treat again. So this correction over here is actually meant to correct for the fact that the main perturbation is not necessarily divergence free. Okay, and we wrote down a set of conditions that this master function big W has to satisfy. So this master function big W has to depend on, say, a vector V and a tensor R smoothly. And then it has to depend on the variables xi and tau. So xi is a fast variable and belongs to the periodic torus. And we derived a set of conditions for this. So first of all, a family of partial differential equations in the variable tau and xi, which at the same time have a dependence on the variable V and R, algebraic dependence. Okay, so this is what we derived. So this is the first condition that we derived. Okay, so then we have the divergence-free condition in the variable W, in the variable xi. Okay, so these are the two PDEs, and then we have two algebraic constraints. One algebraic constraint is that the average of W, tensor W in the variable xi. So here I'm just averaging in the variable xi, which is on the torus. So I'm simply integrating this function inc psi. So this one has to be equal to our R, and the average inc psi of W has to be equal to 0. Okay. Okay, so let me notice the following. In principle, when you're averaging a quantity like this, right? Well, this is a positive semi-definite matrix. So if I'm averaging it, I certainly get a positive semi-definite matrix. And I didn't tell you that there's any property like that for this R over here. Okay. On the other hand, if you go back, right? So here, everything is taking the divergence of something. RQ, we actually expect to be small in C0. So if I just add a constant times the identity matrix, I can actually make my RQ plus the constant times the identity matrix positive definite. And then I don't have to worry about this constraint, right? So here I can just aim at solving this, okay? And of course, the reason why I can do this is that since I'm taking a divergence, if this over here is a constant, and in fact, I can afford even a constant in space, so a function which depends on time only, the divergence will kill it. Okay, and so now the question is actually there, I mean, is there something like a smooth family of solutions of these 4 conditions, which would build this master function big W? And the answer is yes, there is such a family. Although we will see that if we take literally that family, there's something wrong going on. But let us first check that actually that exists. So existence of a family. Okay, so the answer is yes. So first of all, let me actually look at the existence of a family, which is just stationary, which means let me first ignore the following piece. Okay. So if I ignore that piece, my problem becomes simpler. It becomes simpler because what I want is a a stationary solution or a family of stationary solutions of the Euler equations, which satisfy the following condition. Now I'm going to forget that R, actually, I need to add a constant times the identity. I'm just thinking that, okay, so this is positive definite itself, if I have defined it correctly. So it has here average 0, and then it has to satisfy stationary Euler. Okay, and the space of solutions, so the first optimistic remark is that the space of solutions of stationary Euler is actually huge. And there are very classical linear subspaces of the solutions of the Euler equations. So for instance, there are the so-called Beltrami fields. So these are classical stationary solutions of the Euler equations. So they are just eigenvalues of the curl operator. So if you fix a lambda and you take a function which satisfies curl of W equal lambda of W, so this automatically gives you a solution, a stationary solution of the Euler equation. This is something that can be checked. So this one, I'm assuming, is a constant. Okay, and now, of course, you see that if you have 2 solutions for the same constant, you can linearly combine them. And so the question actually boils down to find a sufficiently large space. So for say, to find a lambda, such that the space of fields which satisfy this constraint is a linear space which is sufficiently large. Okay, and then you can imagine that if you have a sufficiently large family which is doing this, you can accommodate for these two algebraic conditions, which after all are just finite dimensional, right? So these two conditions are finite dimensional because if you read them, you see that R is actually a parameter, so it ranges among 3 times 3 symmetric matrices, and so it's just a 6-dimensional space of condition for the first equation and the 1-dimensional space of condition for, well, a 3-dimensional space of condition for the second. So it's a 9-dimensional condition, and if you find a linear subspace, as in here, which is big enough, of course, you imagine you can actually solve that condition. So this is one possibility. But there are also kind of other possibilities. For instance, let me just point out what are called like, Mikado flows. Okay, so this is a very, very simple solution of the Euler equations. So imagine you take like, a direction V, and so this one, let me just call it, it's a direction. So let me just not use V though. Let me just say this one is a direction eta in 3 dimension. Now take, say the linear subspace eta perp. And generate it with some 2 vectors, like say eta 2 and eta 3, orthonormal to eta. So with the property that that span actually this eta perp, and define your function W as simply a cutoff function phi. Well, it does not have to be a cutoff function, but somehow for reasons which are clear later, somehow it would be nice if phi is actually supported on a cross section of the cylinder. So this one is going to be for future reference, the support of phi. So you can take the function phi, say of eta 1 dot x, eta 2 dot x. So it's a function of 2 variables, which is not depending on the direction eta, but it's only depending on the orthogonal variables. And then you go in the direction eta. Okay, and it's very simple to see that this one actually satisfies divergence of W equals 0, but it even satisfies divergence of W tensor W equals 0 directly. So it's even a pressureless solution. Okay, now you want it periodic. And of course, if you want it periodic, what you have to do is you have to choose actually eta in the space of rational directions in such a way that the cylinder, when it's wrapping up around the torus, it actually closes up. So let me just say that this is taken over here. Well, rational. So I guess I want Q over here. And now if I make the support of phi sufficiently small, what actually I have on the periodic torus is essentially a picture like this. So here is the periodic torus. Okay, this one is actually a rectangle, not quite a square, but you see what I want to do. So this direction is like, wrapping around several times. And then, okay, eventually it catches up. And now if I make my cylinder sufficiently small, this will be the support of my solution. Okay, so interesting enough, even this one can be made in a linear space of solutions, because since I am in 3 dimensions, if I actually pick, sorry, just a second. So my laptop has low battery. Okay, let me solve the low battery problem before actually the laptop abandons me. Okay, voila, so done. So since I have actually the three-dimensional space and I can pick directions and I can sort of shift these cylinders in such a way that I don't self-intersect, if I make my support of the cross-section sufficiently small, I can actually superimpose many of these cylinders in such a way that their supports remain disjoint. And if their supports remain disjoint, I can check locally that they are a solution of the Euler equations because there is no interaction, right? So say take several take several different directions. Okay, so now these are going to be like, you know, eta 1, eta 2, eta n, and construct Mikados with disjoint supports. Then take a linear combination. Okay, so again, I'm not actually going to check that. I'm not going to check that it is possible to satisfy this condition. Again, like, you know, intuitively, you just think I can actually pile as many of these Mikados as I want, because, you know, if I make the cross section really, really, really tiny, I can actually combine for 1 billion of them. And if I'm not really extremely unlucky, once I have 1 billion, I'm able to satisfy this, like, you know, 12-dimensional, 9-dimensional space of linear conditions, right? So that kind of seems pretty plausible. Okay, so this still doesn't actually solve the problem that I'm not, that I have ignored the green transport term over here. So I need to solve for this, right? But this is just a linear transport. So say that you have your function Ws, which is a solution of the stationary problem. So let me just go back over here and call this guy Ws. Okay, so what I could do is I could just simply define my W to be the following ansatz. Okay, so I have WVR psi tau, right? And now I'm just going to take this one to be simply Ws of R, because that one is not depending on V. And then I just take psi minus V tau over here, and then tau, right? And now at the same time, when I'm actually looking at the transport part, of course, I will immediately discover that if I take d tau Ws plus v dot grad psi W, sorry, if I'm taking not Ws, but W, right? Times W, that is equal to 0, and that is made equal to 0 precisely by this piece over here. Okay, sorry. The stationary solution is, of course, not depending on tau at all, right? So it's just over here. Okay, so this does the job. And now you have a nice ansatz to plug in into your perturbation scheme, but you will actually notice that there is something wrong, and there is something wrong for which I already warned you in the iteration for the Euler equation for the isometric embedding problem. So let us look at how our ansatz now. What is the shape of our ansatz? So I have VQ plus 1 of xt. So this is equal to VQ of xt. Okay, and now I'm going to have this Ws, right? And now I have to compute RQ of xt. So here I'm good. And then I have lambda x, because I have to insert lambda x in place of psi. So this is what I am actually inserting over here. And then I have minus VQ of xt, and then I have lambda tau. Okay, and now you see that something actually bad happens, and I already warned you about that. There's a fast oscillating term which is multiplying our slow variables over here. So it's not really what we were looking for, because we were looking for something which in terms of RQ and VQ is not going to have any lambda when I actually differentiate in RQ and VQ. So in other words, what I actually didn't write are the conditions or the estimates that I actually want on this multi-parameter family of solutions of the Euler equations. So I should have added at the beginning over here that I also want that when I take the v derivative of W and the R derivative of W, and maybe I have to take, I don't know how many, I mean, maybe one is enough, but I might actually have to differentiate these things even more for technical reasons. So I want smoothness, and the type of smoothness that I really want is that when I differentiate W in V and when I differentiate W in R, I get uniform C0 estimate for this guy. Okay, so remember that I want those C0 estimates on the whole domain that I'm using. I might actually afford to take R on some compact subset and maybe V on some compact subset, because I have uniform C0 estimates along the iteration on these guys. But something which is just locally bounded in the time tau is not going to do the job, right? So because in this slot, I'm actually going to insert a very large time potentially, right? So because tau is going to be lambda times t. So I cannot actually afford that this guy grows in tau. So this one has to stay bounded even if I take very large time tau. And this is obviously something that this ansatz does not do. Okay, so this ansatz here does not do it because, well, if I differentiate in V, I get the differential in V of Ws, and then it's multiplied by tau. And this tau could actually be extremely big. Okay, so it's not really a function which is depending slowly on the variables R and V because of this effect.
Camillo?
Okay, yes?
Hello?
Yes?
Shouldn't this be VQ of lambda t at the end in the last line?
Oh, yeah. Yes, sorry. Yes. That one is a T. Yes, absolutely. Because, yes, as I was saying, so psi, I substitute for lambda x, and tau, I substitute with lambda t. Thank you. Okay, so this does not do the job. And okay, at this point, it sort of looks maybe that, you know, maybe we did just something wrong, right? I mean, we just plugged in some special solution of our PDE problem. I mean, maybe there is a solution which does not have this disease. But okay, now, if you go back over here to the shape of your master equations, right? So you just stare at this object over here. Can you really avoid that this green transport is going to be, in a sense, prevalent? I mean, if I don't have, like, you know, the nonlinear part, then I just have a free transport. So I have to free transport. I mean, the function is going to take the shape some function of psi minus v times tau. That's the only solution of the transport that I know. I mean, there's no other solution. On the other hand, of course, there is the nonlinearity over here. But if you look at it a little bit more closely, remember about this condition, the second condition that I have over here. So this condition is telling you that the average of W tensor W has to be equal to this R plus a small constant times the identity. Along the iteration, this R actually becomes smaller and smaller, right? So this R is actually tiny. So your big W, tensor W, has to average to something tiny. It cannot be something which is big because of this reason. And of course, if you have something tiny and the right-hand side is quadratic, whereas the left-hand side is linear, the linear term is going to dominate. So your solution will certainly look like something like this. There's really no way, you can't really escape this. Okay? So it seems actually that the whole situation is essentially doomed. Except that you can actually go back to your ansatz or to your master functions, and this is like, you know, sort of the first toolbox that I gave you to approach these kind of problems is like, you know, this derivation of these master equations, which like determine the master function big W. But now I'm actually going to give you a second toolbox if there is no solution of this master equation W. Which actually like satisfies the estimates that you would like to satisfy. So remember what you're doing. So you're trying to solve for this. And you can't. Okay, so here it is. What you're trying to do. So you can't do this, and you cannot do because you cannot accommodate for this transport term. Okay, but now you can actually just, you know, observe that at each iteration step, what you actually want to do is you want to get something which is like, you know, closer to be a solution. So it's maybe too much to actually ask for this one to be equal to 0. What I really want at each step of the iteration, I really want to achieve this one to be sufficiently small. Okay, so let me say something like 1 over mu, which I actually decide at each step. So rather than trying to exactly solve your master functions, you actually have the freedom of introducing an extra parameter. And now you have an extra parameter mu q, whereas, you know, you had the oscillation parameter, which I called lambda. That also, of course, is going to depend on the step at which you are in the iteration. So that is like the step lambda q. And you can try to play one against each other, right? So you can try to optimize between the choice of the two. You want both of them large for different reasons. But, you know, before you were actually trying to put mu q equal to infinity. And now what I'm telling you is that, well, you actually have this degree of freedom. And in fact, you have pretty much this degree of freedom in all of your conditions. So I have actually only inserted this over here because this one was the problematic situation. But in principle, I can actually insert this error parameter in any of the other conditions that you're trying to satisfy exactly. So there's no reason for doing that. Okay. And, you know, once you actually get the idea that you can perturb this, there are plenty of ways to find approximate solutions of this system of conditions. So let me actually tell you the first way we come up with. We came up with Laszlo in our first paper. And I'm going to tell you this, it's actually a pretty inefficient way of doing this. So it's not then the way in which the Onsager's conjecture was finally solved. But the reason why I wanted to present it to you, it's because it's extremely efficient in dealing with this issue without actually using too much of the structure of the problem that you have. Okay, so like remember what actually happened. So what happened is that so the ansatz which was wrong was this one over here. But now let me introduce an additional idea. Let me just say, instead of trying an ansatz of that type, let me just try something of the following type. So there would be nothing wrong if I had a solution of this form. So WS of R, right? And then I have, say, Xi minus, and now let me just put here a bar over here. So like, V bar tau, where V bar is a constant. So now this V bar does not have anything to do with the variable V, it's just a constant. Okay, then if it is a constant, of course, I don't have any problem. I'm not differentiating in V bar, I'm differentiating in V, so that's not a problem. But of course, now this guy solves this equation. So it doesn't solve the correct equation. So because remember, you want to solve for V. Okay, but if I look at this, now this one is actually going to be solved up to an error. And you see what the error that I'm doing is. So I'm actually differentiating along the direction V and not along the direction V bar. Okay, and this is going to give you V minus V bar dot grad psi W. Okay, so this is the error that you actually do in your solution. But notice, if V bar is sufficiently close to V, this actually is small. Okay, so I've just told you, for a family, as long as V is actually in a neighborhood of your V bar, I in fact found a pretty decent solution of my problem, which allows for a small error. Okay, so now what can I do? Well, I want this multi-parameter family of W. So I can actually take linear combination of the stationary solutions of W, right? And so what I can actually try to do is I can try to hook up a say partition of unity in the space of V, and now I can try to put the following ansatz for my W. So W of R V, let's say Xi and tau. Now it's going to be like this. So let me discretize the space of parameters V, and let me use a partition of unity on this space. So if this is the spaces of V's, I'm taking somehow a discretization on a regular grid, and then I make a partition of unity over here. So these will be like the supports of my partition of unity. And somehow, if these ones are the direction V bar K, so for each of the direction, I have a function phi K, which is like, supported on that red ball. And I can actually define now my ansatz in the following way. So this is going to be phi K of V. And then I'm going to have some WKS, so some choice of stationary solutions which are different for nearby balls, but in fact, I only have to take care that they are different solutions when there is an overlap between phi k and some nearby phi k prime. So here I need only a finite family of a finite choice of this family of solutions, because there's going to be no interaction between, say, this ball over here, and for instance, this ball over here. Okay. So then here I'm going to have WSK. So here I'm going to have R. And then I'm going to have psi minus V bar K tau. Okay, and now I don't have the problem anymore. So now when I actually plug in this ansatz, right, and I differentiate in V, right, you see that when I differentiate in V, I'm just going to differentiate the partition of unity functions, these guys over here. Okay, I'm not actually differentiating the variable in which or like, you know, the slot which was over here in which the lambda is going to appear. Of course, I have to pay a price for this, right? So if I want an accurate solution or almost solution of my problem, so in other words, if I want this error to be very small, so this one small implies a very sharp cutoff in the partition of unity, which implies that this derivative is going to be large. Okay, but it will depend on this parameter mu q. And since I've actually disjointed the parameters mu q and lambda q, I can try to see if I can play one against each other. So typically what I will want to do is to choose actually the lambda parameter much, much larger than the mu parameter. Okay. So this is just a very cheap way of doing it. But on the other hand, you maybe recognize that it's a fairly general method which might actually work in a lot of other situations. Anyway, so once you have, like, you know, an approximate, you know, an ansatz which actually works, you can now plug it in back into your iteration scheme, which wants to produce a C0 solution. And now it's a matter of checking all the details that this ansatz really takes care of the business. So, and of course, this might be more or less long, more or less nasty, depending on how many error terms you have to handle and how you estimate them and so on, right? So this just becomes like a matter of bookkeeping in terms of estimates. But so what actually happens is that, for instance, this ansatz works pretty well. Okay, so this is essentially a sort of complete description of a way to actually approach this problem, which we believe actually can be potentially applied to other situations. Is in fact the end of the say first part of what I wanted to say. Although it took me, I should have actually ended this like, you know, yesterday, but it took me much longer than I thought. So let me move actually to the second part. And in the second part, we are going to analyze how fast, or better, so how regular are the solutions that such a scheme can potentially produce. Okay, so before actually we do that, let me just point out something that you can do in this particular situation. I mean, now that I've given you an idea of what you can try, you can actually come up with a better ansatz pretty quickly. So let me just simply remark the following, right? So what are we doing? So we want to actually transport our say stationary solution along the flow of the previous iterate. This is what we want to do effectively, right? So what this, like, you know, discretization is doing is just like approximately solving for the transport problem that you had before, right? So I was looking at a sort of you know, solution of this problem over here. Now, instead of actually keeping V as a parameter, let me just put VQ. So first of all, you wanted to solve this exactly. And so one way you could actually directly do this is just to try your stationary solution WS, right, as an initial data. And try to simply transport this along the flow, right? So try to solve for the time function by transporting along the flow. Okay, and of course, you know very well how to do this. So the way you actually want to do this is to define the flow of the vector field VQ, actually and then compute the inverse of that flow, and then map over here with the function, say, let me call it phi. Okay, so what is this phi q doing? Okay, so this phi q is simply doing the following. So here you have your initial data, say, for the ODE. You solve for the trajectories of your VQ, and then you use the method of characteristics. I mean, when you are here at some time t, you just simply go back and solve it for time t equals 0. So what actually is happening is that you're solving the ODE deep psi q of xt is equal to VQ of t psi q of xt. So you're solving the ODE. You have at the initial time the identity, and then your phi q of t is the inverse of this psi q. Okay, so now of course you see that you're running in the same problem as okay, and this one is going to be right. No, this one is fine. Sorry. Now you see that you're actually running in the same problems as before, because if I actually take this ansatz over here and I try to compute what is a derivative in R of this guy, so this is actually pretty fine. So this is not a problem, but ideally what I would have actually liked to have was something like this. So WS of R lambda X, and now I actually have this phi Q, right? So let me actually rewrite this in the following suggested form. So let me rewrite it as lambda phi Q of Tx, and here let me just simply subtract X. Okay, so this is the part that you liked. So this is absolutely the part that you liked. And this is the part that you don't like. And the reason why you don't like this part is because when you actually differentiate this, there is the derivative of the flow times lambda coming in, which is not what you actually devised your perturbation for. So this one actually should be treated as an error. But of course, the derivative of phi q after just a certain amount of time is potentially very big, right? In fact, the derivative of phi q, just by sort of a Gronwall argument, grows exponentially fast depending on how big is the derivative of the function v, right? So typically over here, I have a pretty bad estimate, which tells me that, well, this guy, right? The estimate that I know for this guy is something like the exponential. And actually, let me just put the identity over here, because of course, when I am differentiating this quantity over here, I find the differential of x, which is the identity. And this guy is controlled by the exponential of the L infinity norm or C0 norm of the derivative of Q times tau. So this is a time tau minus 1, right? Something like that. And of course, this is an horrible estimate, right? So VQ is maybe converging in C0, but in C1 it's certainly exploding. And after a little time, my flow is huge. Okay, very well. But what I actually could do now, as before I was actually doing a cutoff in time and space, now I can actually only do, I can do a cutoff which is only in time. So I can just say, well, wait just for a little bit of the time tau until this error becomes larger than a certain threshold. And after that, actually restart your flow with a new initial condition at the time where you got. Because after all, nobody told you that to solve the equation, you actually had to start with the initial condition over here, right? So this was just an arbitrary choice. Okay, I just want to transport along the flow, but maybe at later times I can transport with an initial data which is a little bit before. Okay, and then with this partition of unity, now only in time, you can actually combine your building blocks of the perturbations pretty much as we did actually with the partition of unity in time and space. Okay, so now here what you could actually possibly do is like define flows, say phi i's at discretized times, and they can be spaced by this parameter 1 over mu q. So this layer has size 1 over mu q. And now your function w of r, and then it's going to be x and t. So now this is actually going to take the following shape. So you have a sum, you have a partition of unity, which is depending on the times phi I. And this partition of unity typically takes the shape, say, tau minus ti divided by mu q, right? And sort of these are the ti's. And then over here you have your stationary solution, wi s. So these are depending on r, and then they're going to depend on the phi I. So here you're going to have lambda phi I of x and t. Okay, and somehow now what actually does the job is that phi I, so what you actually do is like, in this lifespan of your, so in this lifespan, in which you're actually switching on your flows phi I, what you're actually asking is that the derivative of phi I minus the identity will be smaller than some parameter mu q. Okay, so this is all good. And in a sense, this is like after you see like the discretization problem or the discretization approach, what actually happens is that this type of ansatz is much more efficient in terms of estimating the errors of what you had before. Like, so for instance, now what you're going to see immediately is that your perturbation W, let me call it WO. So this is the main size of the perturbation of x and t, right? So this is now going to look like this big W of RQ of xt, and then you're going to have, okay, so this is really like, lambda x, lambda t is done this way. So lambda x, lambda t. And what is very nice is that, for instance, now if you do this, when you have a term like dt wo plus vq dot, so this is vq of x and t dot grad in x of this wo. So this term actually would exactly cancel if I am differentiating this part. So it would give me nothing. But of course, what is actually happening is that it is still give me something because it pops into this term over here. So it will certainly give me something like big O of 1 over mu q, right? But it will also give me something because I'm actually differentiating also this guy. So there's something which is going to actually hit this thing. Okay, so plus something which depends on the slow derivative of R, and then there's going to be like, you know, the transport of R. Oh, sorry. So when you are differentiating the phi over there, you actually get over here order of mu q. Okay, but what you actually remember is that when I'm applying, so what will actually happen now when I go back to my original ansatz? So what I'm doing is I am actually constructing VQ plus 1 as VQ plus WO plus this WC that I'm actually ignoring. And when I actually plug in this into the equation, and then I need to invert the divergence. Right, so what is actually going to happen is that I have, for instance, one piece like this. Okay, then I have another piece like this. So let me ignore what is coming from this WC. Okay, then of course I will have a piece like this. Okay, then I have something for the perturbation, which I'm actually ignoring. Of course, I will have a similar structure for my pressure. So something oscillating. Okay. And then still I have, of course, this guy. Okay, and this one I can use the iterative assumption that it's a normal solution of the Euler equation, and I can substitute it with what is RQ. So this is actually divergence of RQ. Okay, and if you remember, in fact, this divergence of RQ was coupled together with this term. So let me actually put them together because there was some cancellation which was canceling the previous error. So here, let me just put it in this way. Okay, and this is going to be equal to the divergence of RQ plus 1. But of course, what we wanted was to invert this divergence operator and so compute the new RQ plus 1. And so now I can just tell you that when I'm computing the new RQ plus 1, I'm going to enucleate 3 different type of errors. So the first one is when the transport operator is hitting my perturbation. Okay, so this is what you might call transport error. There is then when the operator is hitting this part over here. So this is what we call oscillation error. Okay, and then there is the last one, which is what we call Nash error for a reason which I'll explain you in a few minutes, which is this thing over here. Okay, so this is actually what is giving you, like, you know, the size of the next RQ plus 1. And what is the goal of the scheme now? Well, the goal of the scheme is the following. So there are some parameters that you have to choose. So choose the parameter say lambda, which at this point I can actually call maybe lambda q plus 1, and the parameter, which I guess I called actually mu q, but it would be better to call it, well, let me keep it like mu q in such a way that RQ plus 1 in the C0 norm is much smaller than the C0 norm of RQ. Okay, so that's actually what I want to do, and you see that I have some estimates ready to do. So first of all, if I go back over here, I see that I have this big term, like, you know, this which is of the order of mu q. And well, I have also the second estimate. And for this second estimate, it would be really great if, you know, for some good reason, this thing is actually small, right? Now, in first approximation, let us just say that we are going to ignore it, but there is a good reason to actually believe that this one is smaller than just, like, you know, the derivative of the full tensor. And the reason is that, in a sense, you see the same advection mechanism, which actually is already in the Euler equation. So in other words, you see that you're actually advecting this error RQ, which is, however, generated essentially by a stationary solution of the Euler equations periodized at high frequency, and at the same time almost transported by this VQ, right? So this is like the way you actually generate your perturbation. So it stands to reason, after somebody has actually observed it to you, that this one might be much smaller than this term over here. But this was indeed for the first time observed by Phil in his PhD thesis. So this term actually can be ignored compared to this term over here. Okay, now if you do that, when you are, remembered, when you are actually inverting this divergence here, so when you are inverting this divergence, you are actually gaining a factor 1 over lambda q plus 1 because your perturbation is fast oscillatory, okay? So therefore, for the transport error, okay, you imagine there is going to be an error. So you hope for an estimate of type say mu q divided by lambda q plus 1. Okay, so now let us actually look at what happens for the oscillation estimate over here. Okay, so now here there's something like unsatisfactory coming out. So remember, you were an exact solution before of the stationary Euler equation. So if you look at say WS, right, in the old form, and if you remember, WS in the old form was so WS of, say, a certain function R, and then there was going to be a function Okay, so let me just go slowly. So here you had WO of XT. This was equal to WS of RQ of XT. So this was the old ansatz. And now here you had lambda X minus these V bar KT. Let me just make space for the partition of unity. So here there was a partition of unity. And this was depending, of course, on VQ. Okay, so this was in the old ansatz. And now you see what is actually happening. So this divergence of WO tensor WO, right, is something that you liked. So what you really liked was the, say, sum over K phi squared. And then there's going to be, the divergence of the, say, WS tensor WS. So this is something that you like because you have a clean slow variable which is appearing only over here. Okay, and in the fast variable you are exactly perfect. So this is how you devise your mechanism. And so this is actually doing the job that it should be doing. And since this one is actually a partition of unity, the sum over K phi squared is equal to 1. So it's not too much cheating if you're actually putting, say, RQ of XT over here. So it's this would not be really an identity, but remember these phi's are actually peaked on a ball of radius 1 over mu. And this 1 over mu will be chosen like, much, much smaller than the rate of change of this RQ of XT. So at all fx, you can actually think that RQ is almost constant, where your partition of unity, where your function phi k is actually localized. Okay, so this would be actually pretty good. But now there's a bad term, and the bad term is when you're actually differentiating this partition of unity, right? Because sometimes you're differentiating this guy. Okay, when you are differentiating that guy, you're actually going to get something which is like, the derivative of phi k, and then there's going to be like the derivative of VQ. Okay, so fair enough. So this is, of course, not good, and you're going to get a term over here. So when you're actually differentiating this partition of unity, right? So here you see something which has the size, sorry, this is when you're differentiating this other partition of unity. So here you see something that has the size of mu q. So here that is the derivative of VQ, of course, but this one we're just ignoring. We're just saying this is small. But then you're applying the anti-divergence operator, and you're actually finding that this one is lambda q plus 1. Okay, so you have a similar estimate to what you had before. So let me say, so the transport error actually, for the transport error, you had an estimate like that. And now I realize this cannot be a good explanation because one of the two errors actually have to get the 1 over mu q because I need to optimize. So I think I've actually made a small error on the analysis of this guy actually. So let me just look at this guy back again. So this one had a mu q divided by lambda q plus 1, that I was happy. But there must be a 1 over mu q, which is actually coming at that level. So let me actually go back to the transport error again. Okay, so here I was trying to estimate this guy. Okay, so my ansatz was, so this one, right? I had, this one was equal to, so the sum over k. So here I had like, you know, the partition of unity in time. Well, let me just the phi of t minus ti divided by mu. So this was bad when I was actually differentiating in time. Okay, and then I had the ws of rq of xt, and then I had the lambda phi I of x t. Okay, and I'm not seeing the I'm not seeing the term that I would like to see. So when is the 1 over mu appearing? So I don't have a problem when I'm differentiating that guy, and when I'm differentiating this guy, I get mu over lambda. But now I am myself confused on this. Right, so sorry, first of all, this one, the mu actually should appear over here. So that computation was correct. So that term has that error. But it still should be that I'm not solving the equation exactly. So I should see this 1 over mu q actually popping out from some term.
Are the W's Mikados or Beltrami flows?
Sorry?
Are the W's Mikado flows or Beltrami
No,
flows?
no, I'm just thinking about the Beltrami flows in this case.
But then the WS is not an exact solution. WS composed with the diffeomorphism. That will give you a
yes, yes. And that I thought what actually should appear from this computation over here. Exactly. That's what I wanted to point out. Okay, but I'm mixing up. Sorry. Okay, so here's what actually. Okay, sorry. So here's the mistake. So I was actually mixing up exactly. So now I understand. Sorry, I was mixing up the two ansatz. I shouldn't do that, of course. Okay, sorry. So I was actually not analyzing the oscillation error correctly. Exactly. So as pointed out by Laszlo, so here's the problem. So let us go back to our ansatz. The ansatz which I was using actually was not the correct one, sorry. So what I should actually look at is the divergence, okay? And as was pointed out by Laszlo now, so what I should actually look at is the sum of the phi k squared. Now these are cut off in only in time. So let me write them over here completely. So these were the phi of mu, and then here I have t minus ti squared. And this time I actually don't have the problem that the divergence is hitting them because they're just functions of time. And then as pointed out by Laszlo correctly, thanks a lot. So here I have WSRQ of xt, and then I have this lambda phi of xt, and I'm tensorizing with ws of rq of xt, and then here I have lambda phi of xt again. Okay, so now I actually don't have the problem of commuting the partition of unity with the divergence because I'm using this ansatz. I should have been actually I should have paid more carefully attention to what ansatz I was actually using. So now I'm having a problem though. So when I'm computing, now this thing over here, so and I'm actually taking the divergence of this expression. So let me not repeat somehow the variables. So you see that the divergence can actually hit two slots. So when it hits the first slot, okay, there we are actually good, right? And the reason why we're good is because I'm not hitting the fast variable. Okay, but now there's a, so let me just say, so here there's some place in which I'm actually hitting the slow variable and I'm ignoring it. But now what is actually going to happen is that, sure, I am going to, again, to hit a portion that I like. So I'm going to see something like the divergence of this function ws in psi which is this variable. But I also have to differentiate this thing over here, right? And this thing actually over here, what is going to put me in front is something which has lambda. And then unfortunately, it has something which depends on the derivative of the flow phi. Okay, so now what am I actually going to do with this? So this is in principle bad, but remember, I can actually subtract the identity because if I don't have the d phi, then the divergence of psi of Ws, S is actually a stationary solution of the Euler, would actually be equal to 0. Well, if I have to add the pressure, of course, right? So with here, I will also have an addition, which is depending on the pressure, but there is the lambda, and that sort of kills me. Kills the part which is coming from the divergence of psi. But this happens only if I am actually multiplying, so having over there the identity. And you remember what I told you? I told you that for a certain, there will be like an estimate which is coming out on this quantity over here, because I don't want to actually use the transport of I don't want to use this transport when the differential of phi becomes very, very different from the identity. So if you remember, we had the exponential estimate. Now, if I choose my time of existence or cutoff time very small, and this very small, of course, is going to depend on how much time how big is the derivative of the vector field VQ, which is driving my flow phi. So if I actually keep this very small, in fact, the order of magnitude of this term over here will be essentially 1 over mu. Okay. In fact, if you want to be a little bit more accurate, as long as you stay with mu sufficiently small, you can approximate the exponential -1 with the Taylor expansion, which is linear, and the actual estimate is going to look something like this. Okay. So when I'm applying now the divergence inverse, because remember I have to apply the divergence inverse everywhere. Again, because I have a fast oscillation in lambda, I actually hope to kill this one with a 1 over lambda. So the divergence inverse should actually kill this part. So the big prefactor lambda has been killed, and now I see this 1 over mu parameter appearing, which was exactly this idea that I'm actually restarting the flow each time. Okay. So the reason why I was confused is actually because if you take the partition of unity, a trick, and the discretization of the transport, you will actually see this 1 over mu appearing in the transport error. And if you do it instead in this way, you're going to see the 1 over mu appearing in front of the in the oscillation error. Okay. Anyway, so you see what is actually happening immediately. So the oscillation error gives you a term 1 over mu, and the transport error gives a term which is like mu over lambda. Now, the Nash error is even nicer, because if you remember, there is a divergence to the -1, and then there is a WO dot grad VQ. So there is only the derivative of VQ appearing. There is no derivative of the WO appearing. So this one you actually expect to have a 1 over lambda term. Okay. Now, of course, you are at the situation in which you can optimize between, say, 1 over mu and mu over lambda. And when you optimize between these two guys, of course, what you discover is that it seems sensible to choose actually mu like roughly to of the size of lambda to the 1/2, which actually lends you with the combined error of these two terms, which is of the order lambda over 1/2. Okay. Very good. So now let me just try to analyze which kind of course, this is going to give you a convergence in C0, because you can always say, okay, let me now choose lambda really huge compared to the previous step, and I can make my RQ very small. And the reason why is actually converging in C0. So let me discuss first that. So C0 convergence. So if you remember, there was one condition which we always had to satisfy, and the condition was that the average of W tensor W of the master function is equal to our error that we want to cancel from the previous iteration, which is R. Okay. So of course, you can easily imagine that if I'm solving for this constraint, the size of the master function well, let me actually write it in the following way. So the size of the master function, well, this I was doing it for the stationary guy. Well, this one I can actually hope that it is like, you know, the size of R to the power 1/2. Okay, so it happens then something very similar to what was happening in Nash. Of course, this is just suggesting that the size of the perturbation that you add each time, WO in C0, is roughly the size of the error that you wanted to cancel from the previous step to the power 1/2. Okay, so of course, since we are ignoring the correction term, which is going to correct for the divergence-free condition, then what you are expecting from this is a basic estimate of the following type. Okay, and so now you see immediately that if I only have to care about the C0 convergence, the only thing I need to do is actually to make this RQ to converge to 0 sufficiently fast. For instance, an exponential convergence would do the job, and then you would have something summable. Okay, and this is precisely what you can achieve with this rough scheme. Let me just choose, so this one, of course, is of order lambda to the -1/2. So let me just choose lambda huge. This error is actually even much better than the other one. Let me focus on this. I choose lambda huge at each step of the iteration. You give me the error that you want to achieve at the next step. And by choosing lambda sufficiently large, I'm actually able to accommodate for that, right? So essentially, what I'm just telling you is that you can specify what is the size of this quantity over here, and at each step, iteratively, I can choose my parameters mu and lambda in such a way that I will respect that estimate. Okay, and so it's a completely soft argument. Okay, but now let's say that you actually want convergence in C alpha, then now you have to actually start being quantitative. So what happens? So what about convergence, say, in C alpha? Okay. Well, of course, at this point, you want to actually make the sequence converge in some C alpha norm. And if you look at your basic ansatz, for your function WO, right? So there is certainly something which is happening over here. So your basic perturbation takes the form of a function WS, which is fast oscillating at a scale lambda. And you might easily imagine that the C1 norm of this function over here, so in C1, this should be roughly like the C0 size multiplied by this lambda. Okay, so this would literally be the case if instead of having lambda phi of xt, you actually had lambda x. So now you have to take care of the fact that there is this phi of xt. That is, of course, rq of xt, but that is depending much slower on the variables x and t than this lambda would give. But then you also have, like, you know, the assumption that this flow is, I mean, the time of existence of this flow, which is regulated by the cutoff function, which is in front, is only in a span of time in which the function phi is not too far from the identity, okay, in C0 and in the C1 norm. And when you're differentiating, you're actually getting the C1 norm, right? So all I'm saying is that you can regard this entry over here as essentially lambda x plus lambda phi of xt minus x. And under our assumptions, and because of this device with the partition of unity, I'm only interested in x and t, for which phi of xt minus x is actually relatively small. Okay, so with this discussion, you can guess that the size of this error should be something like rq in C0 to the power 1/2, but now I have in front of me this lambda q plus 1 to the power alpha. And now, of course, if I want to devise a system or an iteration mechanism which is converging in some C alpha, I have to pay attention, because I can't simply say anymore, well, let me choose lambda, which is huge at each step in such a way that can accommodate for whichever choice you want for RQ. There is a competition between these two terms, right? So of course I want this one to go to 0. Sufficiently fast, but not at the price of having this one growing up too fast. So I want this one to be growing reasonably slow. Okay, so what can I actually hope for? Well, so here is like the bad news. So certainly this term over here looks like, you know, the least dangerous of them, right? And the reason why it looks like the least dangerous of them is because I have this factor 1 over lambda, whereas over here I have actually the factor which is like 1 over lambda to the power 1/2. Now, this is just heuristics. It's not completely clear, because what is really going to be important for me in understanding what is the Hölder space in which I can converge is what this one over here is. So this one over here actually is not really a 1. It depends on the previous. It depends on the previous step, because it depends on, for instance, the C1 norm of the velocity at the previous step. So if I only want a qualitative result, if I only want C0 convergence and epsilon delta, I can treat it as a constant. And because I choose lambda huge, but now that I want to quantify how big lambda is, I cannot actually just completely disregard what is the size of that 1. Okay, so let me start putting some other parameters over here. So let me just say, you know, this guy over here, let me call it delta q plus 1 to the 1/2. Okay, so that I'm just saying, I'm postulating that for the size of this guy, so this one I'm actually calling delta Q plus 1. Okay, and so now let me analyze how big is this error in purple, even though it's actually the least dangerous error. And that is just to understand what is the boundary that we can achieve, even if we were able to, like, solve the PDE, the transport equation, and combine, like, stationary solution of Euler in such a smart way that we can actually do much better than this 1 over lambda to the 1/2. Okay, so here is what I want to estimate. So that is this Nash error, which is divergence to the -1. And then I have WO dot grad VQ, and I am dividing. Okay, so this is what I want to look at. Okay, so certainly I'm going to gain a 1 over lambda Q plus 1 over here. And that's because this is like the scale of the oscillation, and the anti-divergence is giving me that lambda at the denominator. But now, certainly, I cannot hope to get anything better in front of this than the C0 size of this quantity. Okay, so what is the C0 size of this quantity? Well, it's the size of WO, which is the oscillation that I'm adding. And I already know that this is essentially delta Q plus 1 to the 1/2, right? So remember, the size of WO in C0, we expect it to be less or equal than the square root of the size of RQ. Okay, so here I'm just going to have delta Q plus 1 to the 1/2. Okay, but then I need to estimate the size of the derivative of VQ in C0. Okay, so now for this, since I have this law over here, so this just means that alpha is equal to 1, right? And so you see immediately that what I can expect is that VQ plus 1 minus VQ in C0 is going to, in C1, is going to have a size which is going to be delta Q plus 1 to the 1/2, and then there's going to be lambda Q plus 1 over here. Okay. Now, I cannot hope to get, by this method, a sequence of approximate solutions which is converging in C1. And the reason why we can't hope for this is because we then would land actually on a C1 solution, which looks pretty crazy. And we know that that is not possible because in C1, we have actually well-posedness of the Euler equation, at least for a short time. So certainly I'm not expecting that this converges. And if I am like assuming that there is a sort of exponential ansatz on these numbers, delta Q and lambda Q, of course, what I could just assume is that this C1 norm is exploding exponentially. And this also means that if I want to understand what is the size of VQ plus 1 in C1, this is approximately the size of the last of the C1 norm of the last perturbation that I added, right? So because I have simply an exploding exponential. Okay, so this one is therefore expected to be delta Q plus 1 to the 1/2 lambda Q plus 1. Okay, so now observe, however, that I don't have Q plus 1 here, but I have Q. So my final estimate over here is this. This guy is going to be less or equal than delta Q plus 1 to the 1/2, delta Q to the 1/2, lambda Q, and I'm dividing by lambda Q plus 1. Okay, so this is the size of the estimate, right? And where I am completely ignoring the hard part, which was this one. Okay, and now if I'm ignoring the hard part, so if I were in the ideal case scenario in which the purple part is actually the one responsible for all the error. Well, now to be consistent with my iteration scheme, I need to impose that this number is less or equal than the target size of the next error for my approximate solution of the Euler equation. And the target size is what? Well, it's going to be delta Q plus 2, right? So now, of course, I know that RQ plus 1 in C0 is going to be dominated by this error over here. And so, of course, what I want is that this one is less or equal than delta Q plus 2, which is the size of this guy over here. Okay, so fair enough. Now I actually have a iterative condition which has to be satisfied by these two family of parameters. So the converging size of the error and the exploding size of the frequencies of the oscillations. Okay, and if I plug in if I plug in an ansatz for, say, delta Q and lambda Q, okay, so now let me just say, if I want, so remember that I want over here that this one is converging. So this converges if and only if, so this converges if and only if say delta Q plus 1 to the 1/2 lambda Q plus 1 to the alpha is summable. Okay, if I'm betting on a exponential convergence, then what I can just say is that very good. So lambda Q should then be some certain basic frequency, let me call it lambda bar to the power Q, which is exploding. So this is for maybe lambda bar much bigger than 1. And if delta Q is also going like an exponential, then delta Q should be of the order lambda bar, let me say minus 2 alpha 0 Q. And of course, I would have actually convergence in C alpha. So this would give me convergence in C alpha for every alpha less than alpha 0. Okay, but now I can, of course, plug in this ansatz inside my condition. And the condition was delta Q plus 2 less or equal than, no, sorry, the other way around. So delta Q plus 1 to the 1/2, delta Q to the 1/2, lambda Q divided by lambda Q plus 1 less or equal than delta Q plus 2. Now I can actually plug this ansatz and see what is the value of alpha 0 that I can hope for. Okay, so if I take the log of, if I take somehow a log of lambda bar here, I guess the basis has to be put like over here, right? So if I take a log lambda bar over here, I come up with the following inequality. So lambda Q plus 1 gives me minus Q minus 1. So delta Q plus 1 to the 1/2 gives me minus 2 alpha 0 times Q plus 1. Sorry, there's no 2. So there's only 1 alpha 0. Okay, so delta Q gives me minus alpha 0 q. And lambda q gives me plus q. Okay, and this other guy over here, so this actually has to be less or equal. So this gives me minus 2 alpha 0 times q plus 2. Okay, so now you can recognize immediately the terms in q, actually they cancel completely. So there's a minus q over here. There's a q over here. There are minus alpha 0 q, minus alpha 0 q over here. And there's a minus 2 alpha 0 q over there. And you see immediately that you actually end up with minus 4 alpha 0. And here on the other side, you have minus alpha 0 minus 1. Okay, and you see immediately, if you swap 4 alpha 0 on the other side, this condition is equivalent to 3 alpha 0 less than 1. So you just found that even in the best case scenario, in which the only error term that you have is the Nash error term, you actually have that this alpha 0 cannot be better than 1 over 3, right? So this gives you alpha 0 equal to 1 over 3 as a threshold, which is exactly the conjecture of Gonzaga. Okay, so it looks actually pretty terrible at this point, because let us go back over here. So it seems actually that what you really want is like, the full lambda in here. So any loss of a power of lambda, which is not like, this full 1 over lambda, looks like terrible. Okay, so even if I had like a mu to the power beta over here, I wouldn't actually be able to get to this full 1 over lambda that I have for the Nash error term. Okay, so it looks like a desperate situation. Okay, very well, but let us analyze where our errors actually came from. So if you go back to the mu over lambda error, it actually came from the fact that there is this additional problem over here, right? So our solution of our stationary solution, which was perfectly okay and was actually giving like divergence psi of WS equals 0, is more complicated because it's multiplied by this 1 over mu term in front of it. So by this fact that I'm not having exactly the identity, but I have to actually have this derivative of phi. Okay, so now here it comes the fundamental discovery of Daneri and Zekai-Hidi, who introduced the Mikado flow. So if you remember, I actually insisted that the Mikado flows are pressureless solution. So the Mikado flows are pressureless solutions, which actually means that you can transform them by adding a, say, sort of inverse of this d phi in such a way to kill this term. What is it? In such a way to kill this term. I mean, let me just show you what I mean by this. Of course, so if you have, say, a vector field V, which is divergence free, right? And I am transforming V through a linear transformation AX in the domain. Of course, to preserve the divergence-free condition, I have to multiply by I to the minus 1, by A to the minus 1 over here. Now, this is something that you can do also on matrices. And so there's a transformation which is going to give you the correct correction in such a way that this term over here is killed. So this is, remember, the term that I want to kill. But it's very important that you can use these Mikado flows, which don't have the pressure, because the gradient of the pressure wouldn't actually transform correctly under the linear transformation that you want. So anyway, because the Mikado flows are pressureless solution, actually you can say kill the mu over lambda error. Okay, of course, if you can kill the mu over lambda error at this point, it would look like, you know, the ideal case scenario, because the only error which is surviving is this. Wait a second. So sorry, I'm not killing the 1 over lambda error. Sorry, in this case, I'm actually killing the 1 over nu error. Okay. Okay, so this actually looks like the ideal case scenario. So this looks ideal. Because remember, so now the two errors which you are left with are, you know, the mu over lambda, which is coming from the transport, and the Nash error, which we already know and actually has been quantified. And if you remember, has been quantified by the derivative of VQ in C0, and this actually going to be divided by lambda. Okay, so okay, and then there was of course the size of the whole perturbation, which was WO. But okay, so this thing actually was over here too. Okay, so now remember, I certainly can follow the flow for a certain time, but you remember at a certain point the flow actually starts degrading exponentially fast, and I certainly don't want to go beyond that time. But what is the time after which it starts potentially degenerating in an exponential fashion? Well, this is the time which is proportional to the inverse of the C0 norm of the derivative of the vector field which is driving the flow. So 1 over mu was like, you know, the time that I wanted to follow the vector field, and then I would restart with the partition of unity. So the condition which I just mentioned dictates that 1 over mu, right, is going to be multiplied by the C0 norm of the derivative of VQ. This actually should be of size 1. Okay, but of course, this just tells you that mu is going to be exactly dvq 0 up to constant, and this is what you actually want to insert. Okay, and that would be perfect because this would actually match this error. Okay, so then it would be done. I mean, you would actually have solved the Onsager conjecture because this actually leads you to 1 over 3. Okay, that's the problem though. And the problem is in the following fact. So I was always insisting that I'm going to make some partition of unity, right, in time. So this was my partition of unity in time. And each time I was just telling you that I can take my stationary solution of the Euler equations and, like, you know, transport along these different times, and that would do the job. So that would actually be an ansatz which is good. So that is what I was telling you. But remember that if we are using Mikado flows, so if we are using Beltrami flows, we can simply take a linear combination of any Beltrami flows as long as they are eigenvalues, eigenvectors of the same eigenvalue in this curl of W equal lambda W. So the Beltrami flows we can always actually linearly combine. But if you remember the description of the Beltrami of the Mikado flows, we can combine them as long as the sticks which are defining them are disjoint, right? So the subports of the various pipe flows that we're using has to be disjoint. Okay, so now there's a problem because when I actually apply this phi I, these Mikado flows, which are periodized with lambda, so they're actually very, very like, I mean, they're thin, but they are also like invading the whole space, right? They get actually perturbed by this phi I to something which is highly wiggly. Okay, so now these are highly wiggly. So I start at time, say t0 with my Mikado flows, which are very nice. Then they become wiggly. But now when I actually want to restart with this partition of unity and I want to restart the new transport, I actually have here the straight Mikado from the new family. And I want to superimpose them to the wiggly ones which are transported by the previous flow. Now I run into a problem. I mean, it might be that there is actually no space between the wiggly Mikado flows to put the new ones which start as straight. Okay, so unfortunately, if you actually look at what is happening, this gives you again a restriction that you actually have to choose the typical size of your time of existence of the flow to be much, much smaller than what you would actually need to carry on the program. So it has to stop a little bit, I mean, quite a bit before. I mean, you can't actually allow them to take wiggles which are of size 1 because they are periodized on size lambda. So they can't simply become too messy if you want to accommodate for the next ones to start. Okay, so here is where the brilliant idea of Phil actually came. So I would have no problems if I were to know that my previous iterate has the property that RQ is supported in strips of size roughly dvq C0 to the -1, okay? Because if this were the case, on the time of existence of my flow, in which I actually want to flow my wiggly Mikados, at a certain point, I would actually have no error RQ to kill. So here, RQ would be equal to 0. Since RQ is equal to 0, I actually don't need to add any correction. So I can simply multiply by a partition of unity, which switches everything off. And then I restart actually the new Mikado flows later on. And I can restart them straight because there's no Mikado flows which are coming from before, which have become wiggly. So I don't have actually to care about the overlapping region. Okay, so this is a challenge because, of course, the iteration that I'm doing does not give you such a property, right? So the iteration is giving you something. I mean, even if I assume that I have my RQ, which has this, stripes configuration, the iteration is giving me an RQ plus 1, which does not have this stripe configuration anymore. I mean, it is in stripes, but it is in stripes as big as the one that I had before. And now the dvq C0 to the -1 has become much smaller. Okay, so for this, he actually invented this gluing technique, which, given an approximate solution of the Euler equation, is actually able to cook up a new approximate solution of the Euler equation in which the errors are supported in thin stripes. And in particular, he can do this in such a way to respect the constraints that the size of the error is the size of the stripes is the inverse of the derivative of the C0 norm of VQ to the -1. Okay, so let's say gluing technique invented by Phil to actually achieve this ideal case scenario. And okay, so this is all, well, this is not all I wanted to say, because I had actually in program a third part of the lectures, but I guess I have actually prepared for 3 lectures of 2 hours, not for 2 lectures of 2 hours. So let me stop over here. Thank you.
Thank you very much, Camillo.